in this list, the question is, what is the strongest intermolecular force? Which one is the strongest one? So with each molecule, if you had a sample of this first one, remember that in terms of order, London forces are the weakest. Then you have the just basic dipole, which is the polarity. Then you have hydrogen bonding. Even stronger than hydrogen bonding is the ion dipole. And the strongest of all the intermolecular forces is ionic. So those are like the 5. So weakest to strongest. Correct. So when you look at the first one, you know that it's not ionic because there's no metal. You see those lines, and so you know that it's a covalent compound. So the covalent compounds are the first 3. When you look at this, is this molecule polar or nonpolar? So nonmetals plus hydrogen. So we know that this is covalent. So what do you look at to try and figure out if it's polar or nonpolar? Or NO, F, or what are the 4? What are the 4 electronegatives? Cl, okay? Nitrogen, oxygen, fluorine, or chlorine. If you see just one and it's small, then that means this molecule is going to be what? Polar. 1 chlorine, 1 nitrogen, oxygen, or fluorine, and it's a small molecule, like less than 3 carbons, then you know that it's going to be polar, okay? But there's no nitrogen with a hydrogen or oxygen with a hydrogen. So it can't do hydrogen bonding. So the strongest force would be what? London forces is what you have in nonpolar molecules. It's the dipole. So it's polar. If it's polar, then it is either just the polarity. So remember this side. So this chlorine has its little electrons, pulls the electrons towards it. Up here becomes more negative. Down here then becomes more positive. Creates this polar molecule. So this is the attraction with this molecule is because of that chlorine. So they call this force. If there was 2 of these molecules, they would align themselves, so the slight positive and negative would line up. So what about the second one? All nonmetals and hydrogen, so you know that it is covalent. Is there any electronegatives? Nitrogen, oxygen, fluorine, or chlorine? No. And so if there's none of these, then that means it is nonpolar. And if it's nonpolar, the only attractive force, and it's minimal, the only attractive force is what? Those London forces. Which are really weak. Al2O3. What is Al? Aluminum. And that is a metal. So we have metal, and oxygen is a Non-metal. So metals and non-metals make what? Ionic. So look at it. If it's all non-metals and hydrogen, then you know it's covalent. And covalent will be one of the first three. If it's a metal and a non-metal, then you know it's just ionic. So remember that ionic, they form the crystalline structures, extremely stable. This is the strongest attraction. Aluminum oxide's a solid at room temperature. It's so stable. Melts at a couple thousand degrees. CH3OH. Carbon, hydrogen, oxygens. Is that covalent or ionic? Covalent. Non-metals and hydrogen. So this is covalent. So if it's covalent, then you know it's going to be one of those three. So it has, right, it has an oxygen. So if you see a nitrogen, oxygen, fluorine, or chlorine, then you know that's going to be polar. It has an oxygen, so it's polar. And it has an oxygen with a hydrogen attached. So that's the one where that hydrogen can be attracted to other oxygens of other CH3OH molecules. So this one can hydrogen bond. So notice the one at the top is polar, but it doesn't have a nitrogen or an oxygen with a hydrogen attached to it. So it's only polar. It does the dipole-dipole attraction, whereas CH3OH, that has the ability to interact with other oxygens and has hydrogen bonding as its strength. Na2SO4 in water. What is Na2SO4? It's sodium SO4, sodium sulfate. So sodium is it's a metal. Sulfates, metal and a non-metal, so that is what kind of compound? It's ionic. In water, though, remember those water molecules can surround the sodium ion, the sulfate ions, and help to separate them. So if you see a ionic compound in water, then this is the ion dipole. It's how the water can surround the ions and allow them to separate and float. So those are just examples and ways to pick them out when you look at a molecule. So we'll do this one next time. The last time we were talking about attractive forces in the cell membrane and how polar and non-polar forces create this barrier. So phospholipids, they're the barrier because they have those polar heads, the non-polar tails. They don't allow polar molecules or salts, ionic compounds, cannot freely pass that barrier, which is good because it actually helps to enclose the cell. It keeps everything inside of the cell in, keeps things outside of the cell out. To add stability, that's the little yellow bean-looking things that are in the membrane. That's cholesterol. And then the last one we were talking about was about the proteins. Integral proteins are ones like this one that are found through the membrane. So you can see it on one side and it spans all the way across to the other side. Those act as things like channels, so that's going to control what moves in and out. So polar molecules, like glucose, polar molecules like those water-soluble vitamins, they're going to need to have a channel. They can't freely move through that non-polar barrier the phospholipid creates. And then ions, sodium ions, potassium ions, chloride ions, they can't move through because it's like an oily barrier. But those channels are what allow movement. So molecules can go in or out of the cell as long as there is a channel that will allow them. So just a little more about cholesterol. So cholesterol is considered a lipid. So it's right up there, considered along with your fats and oils. When you look at the structure of cholesterol, it's a 4-membered ring. So it's like 4 rings all fused together. Remember, each one of these is a carbon. So in the skeletal structure, all these are carbon. Nothing but carbon and hydrogen. So very much the hydrocarbon, non-polar. So when you ingest cholesterol, the only place you get cholesterol is from an animal. Okay, animals make cholesterol. In fact, cholesterol is necessary because it helps to make the cell membrane a little more rigid. It helps to make your cell membranes rigid. It also is used as a building block for the sex hormones. So testosterone and estrogen look very similar to cholesterol. There's a couple of things that are added and removed. So in order to make the sex hormones, you also use cholesterol in order to make a molecule called bile. So bile is made by your liver, stored in your gallbladder, and bile is how you actually, it acts like soap. So remember how we were talking about how soap makes the micelle and the non-polar molecules go into the micelle and you wash them away? Well, bile is like a soap that allows your oils and fats in your diet to mix with the watery environment of the body, and that allows them to get absorbed. So we need this to make bile, which helps with absorption of fat. So cholesterol is actually an important thing. This is what the actual cholesterol molecule looks like. The only part of the cholesterol molecule that it has any kind of polar tendency is that alcohol group all the way down on the far end. Everything else is nothing but carbons and hydrogen. So very much like your greasy, waxy types of stuff. But this is the part that actually sticks up around the polar heads. And it's why when you look at the structure of the cell in here, if you zoom in, notice how it kind of looks like the cholesterols, like they're like in the same orientation on one side or the other side. So here's the cholesterol right here. See that little piece sticking up? That's that alcohol group. And that kind of like keeps the cholesterol in this position, keeps them kind of like upright, and they kind of slide right in next to the phospholipids. Some of them point up, some of them point down, but that's what they're actually used for, is they actually make the cell membrane a little more solid. They're not so liquid. They don't break easily. But that little piece sticking up is the alcohol group of the cholesterol. Really. Looking at testosterone and estrogen, or one of the estrogens, see how close it looks? So when you eat cholesterol, it can get converted to testosterone. I just find it kind of amazing that estrogen and testosterone look so much alike. So testosterone is like what causes or triggers sperm production and starts male secondary sex characteristics. Estradiol is one of the estrogens. Same thing, what triggers egg production in the female and also secondary sex characteristics. Not a whole lot of difference chemically between the two, and they do look a whole lot like cholesterol. So cholesterol really gets like a bad rap. So it's most of the time people are like, oh, cholesterol. Like when I was growing up, like this was like the worst thing ever. Okay, so you were like constantly trying to like limit cholesterol intake. But cholesterol, you need it in order to make cell membranes, you need it to make bile, you need it to make the sex hormones. And so when they talk about cholesterol, they measure it in the blood, and they talk about total cholesterol. Total cholesterol should be under 200 milligrams per deciliter. So remember, that was like the same when we were talking about sugar. Milligrams per deciliter, and that's considered optimal. But when you're looking at that, that's actually a measurement of the carriers, because cholesterol is nonpolar. Cholesterol doesn't mix with water, and your blood is water-based. And so you have to have a carrier. So the carriers, there's there's a whole bunch of them. There's really like 5 of them. But there's 2 major ones. The 2 big ones that they look at are HDL and LDL. So when you go, if you get a fasting blood draw done, when you go for a physical, they will send this off and they will actually measure what they call high density lipoproteins and low density lipoproteins. High density lipoproteins, they have the connotation of being the good cholesterol. Okay? This is the carrier that actually takes fat and it sends it to a destination. So it carries fat, lipids, cholesterol to the liver and the body cells for use. So the benefit of it is it's like, so HDL will go and get fat out of fat cells, get cholesterol out of fat cells, and actually take it to like your skeletal muscles so your skeletal muscles can break it down. And so you associate HDL with more fat burning, fat utilization. LDL, on the other hand, the low density lipoproteins, these have been given the name the bad cholesterol because LDL is circulating fat. So these carriers, they just carry fat around. They pick up fat and they carry it along, but they're not like going for a specific destination. So if you have a lot of LDL, the problem can come into play that this circulating fat, lipid, and cholesterol carrier may actually drop some of the fat and cholesterol off as it goes along. So as it moves through the bloodstream, if it drops off, drops fat and cholesterol off, it doesn't dissolve in water, so it sticks to the blood vessel wall. And that begins to develop what they call plaque. So, kind of like your pipes, if you start getting a whole lot of buildup in the pipes, it begins to drain slower and slower. Same thing begins to happen as plaque builds up. Can you see that the inside diameter for blood flow begins to decrease? If plaque builds up and completely blocks this, then blood's not going to be able to continue going. So it basically just closes it off. And so now you got to plug. No circulation downstream. So if this happens in your coronary arteries, which are the blood vessels that supply your heart muscle, then you're at risk for what? Heart attack. So if this plaque builds up and blocks the vessel, what if this buildup occurs in the small arteries that supply the brain? Stroke. Okay, so you can end up having a stroke because it totally blocks it off. No blood goes past those brain cells then. The other thing to remember is that blood vessels are living cells. So the tubes that make up the blood vessels are living. So do you think that the cells that make up that tube are going to get much oxygen and nutrients if there's like slimy plaque all over them? No. So you can even think this wall starts getting more fragile, and that puts it at a risk that it could rupture. And that's the other issue that you have with a stroke. So you can have a stroke because of a blockage, or you can have a stroke because of a rupture that occurs. And so as they begin to understand these carriers, the new thing came out that like, oh, if you have any kind of heart disease or if you have hypertension, then you definitely you should just cut all cholesterol out of your diet. Optimal ratios, when they look at cholesterol values, and this is actually tells them even more about overall health. When looking at the overall numbers, you really want to try and have twice the HDL compared to LDL. So that's really optimal. Most people are about 50-50. Most people have about 80 or 90 of each. But having high HDL means, what are you doing? If you have high HDL numbers, you see that with people that exercise. They have more HDL because they burn more fat. So they don't just burn carbohydrates, they burn fat as like a supplemental energy source. So you find exercise actually increases HDL numbers because your muscles need more energy, and they'll take fat stores, send it to muscle cells in order to be able to provide that energy long term. So there's really a couple of ways. If you go to the doctor comes in and they're like, your cholesterol is 210. Okay, so you know what they're going to do? They're going to pull out their prescription pad and they're like, here, we want you to take a statin. Statins like Crestor, Lipitor, so these are the ones that help to decrease circulating cholesterol numbers. It suppresses cholesterol production. Problem is this. Statins can cause damage to your liver.
So it's killing you either way.
Well, but, doctors get kickbacks and everything, so that's why they want you to write your prescriptions all the time. And so, honestly, the first thing to do, if your cholesterol is over 200, is you try to limit your cholesterol intake. So it's entirely from meat, okay? Animal products. You don't get any cholesterol from plant products at all. In terms of order, beef has the highest cholesterol, then pork, then chicken, and then fish. So in terms of order, and it's really body temperature. Hotter mammals, hotter animals have more cholesterol to keep their cell membrane solid. Fish live in the ocean. If they had a whole lot of cholesterol, they would become solid. Okay, so that's why they have like fish oils and everything. They typically don't have a whole lot of saturated fat. They have a lot more unsaturated because of their body temperatures. So from most to least, that's cholesterol content. So decreasing your cholesterol intake can be one form. The second one, though, is that your body makes it. We're animals, just like the cows and the pigs and the chickens. So we're animals too. We make cholesterol. And some people are genetically predisposed to make more cholesterol than they need. So the next one is to try and actually decrease the effects of this increase in cholesterol. The best way to do that is with exercise. And it's not like you have to go out and start running marathons or anything like that. Like they have actually shown that 30 minutes of exercise every day can begin to increase HDL numbers because the muscle cells are saying, hey, we're having to generate more energy. We need energy beyond what we're eating. And so it'll actually begin to break down fat stores. And that's where the HDL comes into play. Increasing HDL, decreasing LDL, just the random circulating fats and cholesterol, because that's going to help to decrease plaque. Because plaque is really like kind of like the final outcome of what happens with high levels of cholesterol in the blood. If 1 and 2 don't bring cholesterol below 200 and there's a family history of heart disease, so if you had a parent close relative that had a heart attack, and they had high cholesterol levels, and or if you have hypertension, because remember that just increases stress on the heart too, so that's adding to it. So there's really sort of like risk factors, hypertension, plus high cholesterol, plus family history of heart disease. All of those together may require that you take a statin. But that really shouldn't be like the first one to do, just because of the negative side effects of it. All right. So the last part of this chapter, and it's really not, they cover it in the very middle of the chapter, but I find it just easiest if we cover it all the way down at the very end, is all about gases. So gases are different than solids and liquids. So liquids, molecules like roll around each other. Solids are sitting right next to each other. So there's a lot of intermolecular interaction that happens. But gases, remember gases are like this. Right? The odds of two gas molecules coming near each other, slim to none. Okay, so very low potential. Gases, remember, they have a indefinite volume and shape. They take the shape of whatever their container is, and you can adjust their volume if you adjust the size of their container. So one of the things that comes into play with gases that you don't see with solids and liquids are really not affected by pressure. Gases are. So pressure is the force that's exerted on a container. So if you have a sample of gas, these molecules are moving. So they're always moving, and they bounce off the walls. So they bounce off of the walls. The more they bounce off the walls, the more force they exert on the walls of that container, the higher the pressure is. So I just think of that as that this bouncing off of the walls is this pressure. So one place that you hear about pressure is they talk about air pressure. So they talk about atmospheric pressure. Like when they talk about hurricanes and stuff, they start talking about air pressure changes. It's really always kind of interesting to sort of follow all of those. But pressure, if you have, I'm trying to think if I have a, hold on. Yeah, let me add. It's easier to see it if I just draw it. Come on. Okay, so with pressure, if you live at sea level, or if you live like up in the mountains, maybe you live down in a well. So here's us. So at Rocky Mount, okay, we're basically sea level. Like maybe 10 feet up. It's all of eastern North Carolina is super, super flat and is very close to sea level. Why we have so much problems with like flooding. So there is a column of air above you. This column of air is actually creating pressure pushing down. That's air pressure. And when you're at sea level, they say that you're at 1 atmosphere of pressure. So that's sort of the standard. So 1 atmosphere of pressure. But now if you live in the mountains, so if you live in the mountains though, is the pressure greater or less? Less. Yeah, because here's your column of air. So the column of air above you is actually lower. So there is less air pressure. Now, you know when the weatherman talks about a high pressure and a low pressure zone. High pressure zone is when there's not a lot of moisture in the air above you. And so there's like more air, so it creates more pressure. So that's what a high pressure. High pressure is almost always associated with drier air. So it's associated with like not rainy weather. So high pressure is the dry air. Whereas when they talk about a low, they're like, okay, well, a low's moving through. That's like when your fronts move through. When low pressure, in a low pressure system, there's more moisture in a low pressure system, so there's less air molecules. And so that's going to have less pressure. So that's really the difference between them. When they talk about high pressure, dry air, low pressure tends to be wet, like a wet air, rainy, that type of weather change. And with hurricanes, right around that center of their circulation, they measure that pressure. And so when the pressure starts to drop, that tells them just how intense the movement of that air is and how much moisture is in there. The lower it goes, the faster the wind speeds are, the worse the storm itself is. So when they talk about it dropping and dropping and dropping, that's when everybody starts getting really excited. But that's your weather. Now, if you lived below sea level, so if you were a miner, okay, you would actually have more pressure. Okay, so if you live below sea level, you would have a higher air pressure. And this really doesn't come into play to any degree in North Carolina just because we don't have a huge fluctuation. But if like you lived in Denver, Denver is a mile above sea level. So that is a pretty significant elevation. And so there's less air pressure. So here, water will boil instead of 100 degrees, which is what happens here. Water boils at 100 degrees Celsius. Here, water will boil at like 94 degrees Celsius because there's less pressure pushing that water in, and so it becomes a gas with less energy. So water boils, and that can affect like cooking. Okay, so they'll have like high altitude directions on some recipes and things like that, and that's because of that lowered air pressure. So they use this, and it's called a barometer because it measures pressure. And if you ever had I can remember one of these on the wall in my doctor's office. So there was a big, long column of mercury attached to the wall, and that's what he would use when he used to take your blood pressure. So they take a pool of mercury, they take a column that is 760 millimeters long. They fill it with mercury, and it's a tube, like a really long test tube. It's about 1 centimeter wide. They flip it upside down into the little pool of mercury, and so it creates a vacuum. So up here, there's like no gas molecules, but the pressure of the air pushing down on that pool of mercury will cause the column of mercury to go higher or lower depending on that pressure. So when pressure is high, the column of mercury is higher. When air pressure is low, the column of mercury, there's less pressure pushing down, so the column of mercury drops. And so that's how they can actually measure barometric pressure. So we talk about millimeters. So you can have mmHg. Where have you seen mmHg? Blood pressure, right? So in your blood pressure readings, it's always millimeters of mercury. That's what mmHg is. When they talk about 1 atmosphere of pressure, 1 atm, it's equal to 760 millimeters of mercury. So what they mean by that is that's how tall that column of mercury would be at 1 atmosphere at sea level. Weathermen oftentimes talk about it in inches. So they'll talk about if they don't use millimeters of mercury, they talk about it in inches and the mercury rising or falling. So there's 2 laws that we're going to talk about that relate what gases do and how pressure, volume, and temperature are affected. So the first one is called Boyle's law. So Boyle's law, this was something that was like hypothesized and research was done a long time ago because they didn't have to have like pure elements. They could just take samples of different types of gases and run these tests. So this was like 1600s. So Robert Boyle, he looked at chambers that contained gases, and measured pressure. So he found here, so we have these little gas molecules inside. So he said, well, if I take this syringe and it has this volume, we'll say that it's like a 3 ml volume. Each little dash is like a milliliter. It's just a little 3 cc syringe or a 3 milliliter volume. If I put twice the pressure, so if I push twice as hard on it, that will, doubling the pressure, what happens to the volume? By how much? Half. And if I take that initial 3 milliliter volume and I push with 3 times the pressure, what happens to the volume? Instead of, so looking at this last one, if I have 3 times the pressure, I'll have 1/3 of the volume. So we saw that they were related. If I change the pressure, the volume is going to change by an inverse proportion. So breathing is a good example of this. So in breathing, you have 2 steps. You have inhaling and then you have exhaling. So inhaling is actually a very active process. Inhaling involves muscle contraction. So you have the muscle that splits your thoracic and abdominal pelvic cavities. That's the diaphragm. So normally at the beginning of an inhale, the diaphragm is relaxed, and when muscles relax, they lengthen. So this muscle is sort of like bounces sort of more up. When it contracts, it's going to get smaller and drop down. So you can see that the change that occurs, so the diaphragm is going to move downward. You also have muscles between each rib, and those are the intercostals. So the external intercostals actually pull your ribs up and out. So if you've ever measured somebody's respiratory rate, you watch their chest and you just watch it rise and fall. So that movement, the external intercostals pull the ribs up and out. So you can see their ribs look like they go up. So what's that going to do to the volume inside of the thoracic cavity? So we're going to increase the volume. But like we said with the syringes, if we increase the volume, what's that going to do to the pressure? Will it increase or will it decrease? That's going to decrease the pressure. And this is all inside the thoracic cavity. The only way to balance the pressure is to allow air to flow in. So that's pretty convenient because you've got the lungs, and as they begin to fill with air, the pressure will rebalance. And so the amount of chest movement will affect just how much air gets pulled in. So when you do a deep breath, you can really feel like your ribs moving up and out. That diaphragm drops all the way down. But if you just do a quiet respiration, ribs don't change very much. The ribs don't change in terms of contraction. So by adjusting the volume, you adjust the amount of pressure change that occurs, and that'll affect how much air gets pulled in. So now you're at this inhale, at the top of an inhale, and then you go to the exhale part. So this pulls air in, creates like a negative pressure, which is really like suction. With the exhale part, though, this is really relaxation. So when people snore, they usually snore on the inhale because they're trying to pull that air in. But then when they're exhaling, it's like, so everything just relaxes. So the diaphragm relaxes, the intercostal muscles relax. And so if these muscles relax, they're going to allow the ribs to drop back in, allow the diaphragm to move upward. And that's going to then start to do what to the volume? So it's going to decrease the volume. So if the diaphragm moves up, ribs move in, volume inside decreases. What's that going to do to the pressure? So the pressure is going to go up. And the only way to allow the pressure to balance is to push air out. So this increased pressure pushes air out. So I found, and maybe it'll work, I found North Carolina School of Science and Math, that they did a Boyle's Law demo, and so I think this is so cute, because it's a peep, okay? So what they did is they put a peep in a vacuum, oh gosh, what do they call it? So it's like a vacuum dome.
Vacuum jar.
So if you watch,
the marshmallow
so they sit them on,
air
and then see the red tube that's off to the side. So the red tube that's off to the side is going to pull suction. Okay, so it's going to start to decrease the pressure inside, and you'll see the changes that occur.
As we apply the vacuum, the pressure outside is lower than the pressure inside. The air in the peep will expand.
Okay, so they
to
decrease the pressure, and what does that do to the volume of the marshmallow?
When we release the vacuum, the pressure increases and the volume decreases.
Decreasing the pressure increases.
As another illustration of
the other
Boyle's
one,
law,
if you look,
we'll put illustration of Boyle's law. As another
yeah.
of gelatin and sugar.
So in this first one,
as we apply the vacuum,
they're now creating suction.
The pressure outside
so they're pulling air out, decreasing the pressure,
inside.
increasing the volume.
The air in the peep will expand to try and equalize the pressure.
They're pushing air in,
when we release
so that
the
acts
vacuum, the
as
pressure
increasing the
increases
pressure,
and the volume
poor little
decreases.
peep's like,
as
looks
another
like
illustration of
this
Boyle's
is
law,
shaving cream.
We'll put some shaving cream.
So you put
into
shaving
our
cream in a
vacuum
beaker,
jar.
starts
the
to pull
shaving
suction,
cream contains
pressure
air
goes down,
trapped in a
volume,
soap mixture. As we apply a
volume
vacuum,
goes up. And it'll
the
keep
pressure
going.
outside is lower than the pressure inside.
As long as you're lowering the pressure, the volume goes up.
The pressure.
So they're like, they say they're inversely
As you decrease
proportional.
the pressure,
Pressure
the volume
goes up,
increases.
volume goes down. Volume goes up, pressure goes down. So you can give
gas.
Uh-oh.
It's all around you. It's in space. It's on Mars. It's dissolved in your blood and in your soda. It's their behavior.
We're talking. Okay? So there is actually a calculation that you can do if you know the pressure and the volume, initial or final, and you know a change in pressure or volume, you can solve using this ratio. So this is Boyle's law. So in this, P1 times V1, so this is times, is equal to P2 times V2. So the initial pressure times the volume would be equal to a change in pressure and its final volume. You will always know 3 of the 4 numbers, okay? Key things to make sure your units are the same because they can't cancel if they're not the same, and make sure that you set up the problem. So here's the way that I do this. So if a sample of gas changes from a volume of 82.3 liters to 26.5 liters, what was the initial pressure if the final pressure is 1,825 millimeters of mercury? Okay, so you've got 3 numbers. If you see that we're talking about volume and pressure, then you know this is Boyle's law. So look at what your question is asking. If you see volume and you see pressure, then you know it's Boyle's law. And so P1 times V1 is equal to P2 times V2. Sometimes they call it initial, sometimes they call it final, like you could say P initial times V initial is P final times V final. Either way, then the next thing to do is assign what is each thing. So do you know P1? Okay, do you know, so P1 would be this on this side is the initial, this over on this side is final. So you don't. So this is your question mark. Do you know V1? Okay, 82.3 liters, right? So the sample of gas changes from a volume of 82.3, so that's the initial, Okay, so do we know P2? Pressure. 1,825 millimeters of mercury. And do we know V2? 26.5 liters. Okay, so we need to find P1. So if we have P1, V1 is P2, V2. What do you do in an algebra equation if you need to get something all by itself? How do you get P1 all by itself? What are you going to move? You want to move V1, okay? So if I want to move V1, how do I move V1 from the left over to the right? Divide both sides by V1, right? Remember, you can do it the same. You can do the same thing to both sides of an equation. So this and this then cancel. That's going to get P1 all by itself. So I always rearrange the formula because now all I have to do is plug in the numbers. Okay, so I figure out, okay, which one don't I know? Which one do I know? And make that as a list. And then which one do I have to get all by itself? Rearrange the formula and then just plug it in. So P1 is equal to, what's P2? 1,825 millimeters of mercury times V1, V2, which is 26.5 liters, divided by V1, which is 82.3 liters. So you notice that liters and liters will cancel, leaving you with an answer that's in millimeters of mercury. So 1,825 times 26.5 divided by 2.3. Yep. So P1 is 587.636695 millimeters of mercury. Can I keep all that? No. How many significant figures do I want? Look at the problem. Okay, so the 82.3, 3 significant figures. 26.5, 3 significant figures. 1825 is 4, but remember with multiplication and division, you always take the smallest number of significant figures in the problem. So I need to round this to 3. So I will keep the 5, the 8, the 7. That means everything next has to get rounded. So that 6 does what? So 588. Okay? So just look at the problems in the question. The number of significant figures tells you how to round. So if it's pressure and volume, then you know that it's going to be Boyle's law. Assign each of the units to figure out which one you don't know. Rearrange the formula, and then just plug it in. And look back at your problem to figure out how many significant figures in your answer. Okay? So do one more. So if the pressure of a sample of oxygen changes from 2.5 atmospheres to 6.4 atmospheres, what will the final volume be if the initial volume was 0.025 liters? Follow the same steps, set it up. Okay, so in this one, what is V1? 2.5 ATM. What is P1? Wait. Yeah, I have them written backwards. 2.5 ATM. And V1? 0 to 5 liters. So V2? That's the final volume. And then P2? All right. So I want to get V2 all by itself. Which do you move? So if you divide both sides, that'll cancel, moving it to the other side. So then it's just a matter of plugging them in. So 0.025 liters times 2.5 atmospheres divided by P2, 6.4 atmospheres. How many significant figures? So I got 0.00976565. Atmospheres cancel, so I have liters. What everybody got? Yes? Okay, so 2, I keep those zeros out front. Remember, leading zeros, you need them because they show the size. But here's the first 2 significant figures that I come to going across is the 9 and the 7. So that means, what's going to happen? 0.0098 liters. Okay, so that 7, the last significant figure, gets rounded up because the number that's going to get dropped is a 6. Okay, so there is one other one. So this one's Charles's law. So Charles's law doesn't use pressure, so you got to keep pressure the same with this one, so no using a vacuum or anything. But in this one, it's changing temperature and changing volume. So in temperature and volume, they found that if you take a sample of gas and you heat it, what happens to the volume? So if you take a sample of gas and it starts to heat, is it going to shrink or expand? It expands. Okay, so my example of this is what happened on the regular with the birthday balloons. So I have 2 children. I mean, one of them's 30 now. But one of them had a birthday at the end of August. So the end of August in eastern North Carolina, hot as blazes. But one of the sort of traditions that we did is on their birthday, they got as many balloons as they were old. So when they were 5, not a big deal. 5 balloons, bringing it home, 6. But then they were like, this is a tradition, Mom, you have to get us balloons. So I was bringing home 16 balloons at some times, okay? So like the worst case scenario though, the one one's the middle of June, the other one's the end of July. And so where do you go when you have to buy 14 balloons? You're not going to Harris Teeter. Okay, so if you have to buy 14 balloons, where would you go? The dollar store. Yeah, go to the dollar store. All their balloons are $1. Okay, so I'd go and I'd get 15 balloons. The problem is, 1, getting out to the car with 15 balloons, trying to get through the door. Okay, but what happens in the car? What happens? So I drive to the dollar store. That's not such a big deal. Turn the air conditioner on full blast because it is like blazing hot at the end of August. So birthday in the summer. So the car sits in the parking lot because 15 balloons, it's going to take them a while. Okay, so I'm in there, 15 balloons waiting. Like, you know, just sort of, and it's the summer, so everybody moves just a little bit slower. So car in the parking lot on hot pavement. What starts to happen to the temperature inside? So in the summer, temperature increases. So it may be, especially like with the sun and on the hot pavement outside of the dollar store. So I finally get all my balloons in, get them loaded into the van, get the van shut, okay. I get in, start the car. So it's now hot in the car. So I start it and I turn the air conditioning on full, but all the balloons are in the back. And then I have like the mom van, so like it's got all of the big windows and everything. And so inevitably I'd be driving down the road. What would begin to happen to the gas inside of the balloons? They begin to actually expand. Yes, so I'd be driving down the road and they'd be like, pow! like, oh no. And then I'd bring them in and they'd be like, wait a minute, there's not. And I'm like, there's the busted balloon. I'm like, well, I lost a few. There's some casualties in this one. But that is because it would actually cause that expansion. So hot air, temperature increases, the balloons expand. And since they're freshly blown up, they're usually nice and tight, so there's not a whole lot of expansion that they can actually do. So in that one, if you increase the volume, you increase the temperature. If you decrease the volume, you decrease the temperature. So see how this is like the opposite of Boyle's law? Boyle's law, if one goes up, the other goes down, right? Increase volume, decrease pressure. This one, if one goes up, the other goes up. If one goes down, the other is going to go down. So here's the little video for it. Not that one, it's this one. So the Charles law experiment.
We're about to perform an experiment of Charles's law.
Is nowhere near as exciting.
We'll be inside the flask.
So what he does
is
he takes a sample, a flask, and he dips it into boiling water.
Up to the same temperature as the boiling water bath, there will be just enough
air
in the flask to fill the flask at the boiling point of water.
He's going to pull that out.
I'll put my fingertip over the tip of the glass tubing and the rubber stopper to trap the air in the flask. I will then quickly invert the flask in the tank of water and allow the gas to cool. As the gas cools,
see what happens? So as the gas inside of that
will
flask
push water up into the flask. Eventually,
the
air in the flask will come to the same temperature
so you can actually
as
see when
the
it cools
temperature in the large water bath.
It's taking up
we'll
less
raise the
space.
flask so that the water level inside the flask
So
and
you
outside
can do it with
the
any
flask
different
are the
types,
same.
like he even does it with
This
like
means
a
that the
big
total
liter flask
pressure
or
in the
1.5.
flask will
Any
be
one
the
that
same
you do,
as
you're going to
atmospheric
end up
pressure.
having this as the result. So in
I will now
ours,
put my finger back over the tip of the stop.
but the same, irregardless of the size of your, irregardless of the size of the flask, increase volume increases temperature. Decreasing temperature will decrease volume. So they go the same way. So they say that this is directly proportional. There's just one caveat, one problem. As they started trying to study gases, they came up with the problem that, and in this one, we have degrees Celsius. But what if you take a gas and you chill it below 0 degrees Celsius? Then you start with a negative number. And negative numbers increase as you go down. And so they found that they could not use Celsius as the temperature scale. So temperature, if you see temperature and volume, then you know it's Charles's law. Temperature and volume is Charles's law, but there is that one criteria. Temperature values cannot have a negative number. You cannot use Celsius because you could potentially have a negative Celsius number. So they're like, well, we have to like take out this negative factor. So somebody sat down and started doing some calculations and calculated what is the coldest possible temperature that we can get. What is the temperature? Remember that temperature is like a measurement of the vibrational activity of molecules. So what's the temperature where molecules literally stop moving? So they called that absolute zero. This is the coldest possible temperature. But they kept the Celsius scale, which is nice. So it's really easy to convert from Celsius to Kelvin. The Kelvin scale, it is minus 273 degrees Celsius. So 0 Kelvin is minus 273 degrees Celsius. So if you want to go from Celsius to Kelvin, you just add 273. If you want to go from Kelvin back to Celsius, just subtract 273. So in looking at this one, V1 over T1 is V2 over T2. What is V1? That's the, what was the initial volume? That's the question mark. So what was T1? So the initial temperature is 25 degrees Celsius. V2? And then T2. Okay, so just like before, just look for, identify what is each of the units, which one don't we know. Before you go any further, convert it to Kelvin. So the temperature values, I need to go to Kelvin to Kelvin. In order to do that, you go from Celsius to Kelvin, just add 273. So 25 plus 273 is 298. (105) Celsius plus 273 is 378. I think I got that right. Okay, so those are my temperature numbers. So the last thing I got to do is I got to solve for what? V1. So that means I got to move what? So see, I got to get V1 all by itself. I've got to move T1. So how do you move T1? If I multiply both sides, by T1, that will cancel. And then you just plug them in. So V2, 24 liters times T1 in Kelvin, 298, divided by 378 Kelvin. So see that Kelvin and Kelvin will cancel, leaving you with an answer in liters. About 18 with a whole lot of decimals. How many? So what you want to do is always look at your numbers up at the top, because those are the measured numbers. And so 24, 2 significant figures. 105, 3 significant figures. 25, 2 significant figures. So you're going to round to 2. So that's the 1 and the 8. So it'll end up being 19. Since the next number that I get dropping off is a 9, that means that the 8 becomes the 9. 19 liters.
So if this is a question on a test, I mean, I assume we have to solve it, but will we have to tell if it was Charles' law or Boyle's law?
That's the, if you check if it's pressure and volume or if it's temperature and volume, then that way you know you're going to use the right formula. Okay, so that's kind of like the first step. Which formula am I going to need? Do I have pressure and volume, or do I have temperature and volume? And then set up, so that way you like write down your formula, write down what each unit is, figure out what your unknown. You'll always have 3 out of the 4. So it's really just figuring out, okay, which one don't I know, and then just plug in the rest of them. And then solve for the one you don't know, and then double check your significant figures in your answer. Okay, so I'll let you do this one. Okay, so you know that this is Charles because it's volume and temperature. V1 is 12.5 liters. T1, 15.5 Celsius. V2, you don't know. T2, 89.5. Okay, so before you go any further, what's the next thing you have to do? Yeah. So this, if you take 15.5 plus 273, 288.5. If you take 89.5 plus 273, it's 362.5. And that's K. They don't even put a degree, they just say K. I don't know like it, but. Okay, so now we got to solve for V2. So how are we going to get V2 all by itself? To move it, since it's in the denominator, you put it in the denominator on the opposite side. So remember, that means that those two will be multiplied. They're on the top. So then it's just plugging it in. So 362.5 times 12.5 divided by 288.5. So 15.7 liters. So I had 12.5, 3 significant figures in my number, 15.5, 3 significant figures, 89.53. So that's where that answer is going to end up rounding to 15.5 liters. It's not terrible. Just a matter of like reading through, figuring out what unit means which. Do make sure you double check. Anytime you've got temperature, you've got to use Kelvin in it. So those are really the ones that we are going to use. There are other ones. We're really not going to spend much time on them. What time is it? It's close enough. All right, so on Wednesday, we're going to talk about Chapter 8. So Chapter 8 goes through solutions, mixtures. We've been talking about that in lab, working on those, making up solutions and such. So we need to talk about just sort of general characteristics of solutions. So we'll talk about true solutions, colloids, and suspensions. And we're going to talk about how concentration is determined. So about things like molarity, percent solutions, and such like that. Okay, so we'll pick up that on Wednesday. Next Monday is Veterans Day. So I will give you your take-home exam this Wednesday, and you will have until the Monday after Veterans Day to finish it. Okay, so it'll really give you almost 2 weeks, but that way you'll have that time and you have the holiday, because I didn't want to give it to you the Wednesday. I'd rather have it get passed back in by that Monday. I was trying to think. You can do, there's a gas laws dynamic study module. We're completely done Chapter 7, so you can work on the post-lecture ones for that. And then start looking at Chapter 8. And I did open up the pre-lecture for Chapter 8 till Wednesday, so if you haven't done it, go ahead and get it done.